as Jerry said in the previous hour, I've been with him doing a bunch of research on this for a while, figuring out what's really essential about how to build these kinds of propagator networks flexibly and how to, ideally, how to be able to construct a programming language infrastructure out of such an idea. But along the way also, if you can figure out how to build them for specific purposes, then that's good too. So hopefully has convinced you that this is a good idea to be interested in, because I don't really have any motivation in this talk besides that slide. And I guess I also prepared a recap of what they are. Well, the only really interesting thing about this is a little bit of notation in case the function has arguments that aren't commutative. I'm going to have a little black circle for the second one. So I have this little machine. Conceptually, you want it to sort of always be on and always examining its neighboring cells. And as soon as there's an x in there and a y in there, it can spit out an f of xy over there. And if we stick a bunch of them together, then in this state, none of these machines can do anything because they don't have enough inputs. But if, say, a 68 comes in over there from someplace else, now this guy still can't do anything, but this guy can. And so off he goes. Now he's done, but that guy can do something. Off he goes. And that's sort of why they're called propagators. One thing we'd kind of like to have is for the cells to be the repositories of state, and for the machines to be stateless themselves, so that the cells are our names for the values that can change, and the machines are just these things whose essential structure, that is the function they compute, is the only thing that's interesting about them, and it never changes. Anyway, if we could build machinery like that, then we'd be winning in various ways. Multi-directional constraints come out very naturally as just piles of mutual inverses. So if we have a little collection of propagators like this is a sum constraint. If any two of these cells get filled with values, then one of these three machines will have enough inputs to go and can fill in the third one. If there's a 1 and a 2 there, then the plus can put a 3 there. But if we didn't have this 1 and had the 3 and the 2, then that minus could put a 1 in here. So we can we can stack these unidirectional propagator machines on top of each other to get multi-directional constraints if we want. And constraints are nice to have. There's been lots of work on building constraints directly, so it's kind of pleasant that this propagator idea can recover them if we do it well. For example, if you want to convert between temperatures, it's a fairly canonical example of an algebraic expression. The constraints just compose very naturally. If somebody gives you a Fahrenheit on one end, then the sum constraint can deduce what the difference is, and then that product can do that thing and go that way. On the other hand, if you get a Celsius instead, then it can just as well go the other way. And we don't have to do any work to manually invert this larger function because it's built out of things that already have their inverses there. And it very naturally extends to Kelvin. And we don't have to think about separately writing a Fahrenheit to Kelvin converter or a Kelvin to Fahrenheit converter. And we don't have to adjust any control loops that are explicit because the control loop is implicit. It's inside the choice of which propagators to run.
So if you have a computation which uses an input twice, then you don't get the inverse for free.
Yes.
Okay.
So is this the bit of this whole scheme that accepts
What?
Is this the bit of this whole scheme that Excel does not have?
Excel has the minimum possible thing. This is one of the things it doesn't have. I'll get into later what happens if you draw a few more of these around here and have a loop that goes over there, so you have multiple different ways to get the same thing.
If Excel can deal with
What?
Because
It
some
can't?
equations and stuff.
All right, well, there are various things that are like that can't. And does it run?
It
Well,
iterates convergence. He says it iterates convergence.
Excel.
That's the
Yeah.
test. He's going to talk about
it's possible to build this thing so that instead of iterating to convergence, it can trace a symbolic value through it and then solve the equation. Sometimes that works better. But I'm not going to talk about that in detail because that's really hairy. But, another win, if we get this to work, is the good backtracking, like Jerry was talking about. So in order to do good backtracking, having a propagator network is the part that lets us jump back to the right choice and not recompute things we've already computed. Well, we still need to do the other things. So if we teach ourselves to store values that are justified by names of guesses, so that's 3 because somebody named A decided that that ought to be 3, and maybe this one is 2 because somebody named C decided this one is 2. So it needs being a propagator network doesn't solve that problem. That problem needs to be solved separately. And we also need to adjust the primitive operations in an appropriate generic way so that they track the dependencies. So this is a less than, maybe it's some generic function such that if it sees a data structure with a colon in it and another data structure with a colon in it, it can do the computation on the first part and union the dependencies, then it can put a true supported that depends on the choices B and C in here. And we also add appropriate boxes that enforce requirements. So this is a box that insists that the value be true, which in this case it is. That's fine. But now what happens if it doesn't work? So that minus can make us a -1 over there that goes through the abs. And eventually comes out with a true, but abhor is a box that wants the answer to be false. So the abhor can examine the dependencies that we've accumulated, which are the names of the choices we've made, and decide that A and B together cause a contradiction and maybe memorize that somewhere. And then have everything that, and maybe it decides that we want to undo A. So one way to do this is to have some global variable that's the worldview, so there's some magical process that says, all right, the A choice is now out, and get rid of the values that depended on A and B because that's a contradiction. We know we don't need those anymore, but maybe we remember the 3 because maybe later we'll want to believe A again. So this gives space to try something else. Maybe whatever decision maker had originally thought 3 might now choose 1 with a different premise. And then that computation can propagate through there, and now the abhor is satisfied. And in going through all this, we didn't have to recompute any of this stuff because it didn't depend on the A that we decided to unmake. So that's a big win if we can get that. And this sort of remembering the no-goods, if the things that make the choices are aware of what the no-goods that have been discovered so far are, then they can avoid making a choice that is already known that will cause a problem. So for instance, if we later decide to disbelieve B and then rebelieve A, and then the B chooser is choosing again, it can look at that no-good and say, well, no, B is not a good thing. We should do something else.
Yes, here's a question.
Would you clarify the justifier decision maker labeled with the ABCD?
for example, A only says that that top left spot
Yeah.
should be 3.
Yes.
It'll never say that top left spot should be 4 or 7.
Yes, that's the idea.
Okay.
Yeah, it's that,
Um,
the name is not the name of the decider, but the name of the decision.
Okay. Thank you.
It's the
Yes.
choice.
Yep.
So depending on how you implement it, there could be the identity of the decider could be implicit in this notion that if none of its choices are possible, then it will do something weird, perhaps. And there are lots of different ways to do this, which is why it's a good idea to pull out how you do the backtracking from the idea of how you do the propagating. Those are separate. And I don't know whether we have the right theory about how to do the backtracking. This is just one way to arrange it. This global pile of no goods is convenient, but global. That's not a good idea. So that was the good part. Now for the bad part. This cell right here has 2 propagators staring into it. If an input comes from this side, it'll get an answer from this one. If an input comes from that side, it'll get an answer from that one. What if it both happens? So historically, these systems have generally been built with the implicit idea that the cells are things that hold values. And then if a cell is a thing that holds a value, then what do you do when you get a second value? Well, it might happen. There are computations that are multidirectional. We wanted them to be multidirectional because we want to be able to send Fahrenheit to Celsius or Celsius to Fahrenheit. But what happens if we do both at once? Well, and it seems to me that the previous efforts have generally foundered in this place in one way or another, because none of the available choices are good. This idea that a cell holds a value messes you up sort of inherently. But let's see why. What are your options for what to do with a second value? Option A, nothing. Well, that's not very good at all, because you had something that was a constraint, but you got a 1 and a 2 there from the outside, but before the plus could put in a 3, somebody else put a 6 up there. That could happen, right? Well, if the plus tries to put in the 3, that cell already has a 6. You give it a 3, it goes, okay. So you have a constraint that didn't constrain. That's not good. Can't do that. We could always override. Whenever there's a new value, it clubbers the old value. We forget about the old value and go on with life. Well, that's not a good idea either. We tried this, but you get a 1 there, you get a 2 there, so then the plus can produce the 3. Wonderful. 3 got added, so now, whoops, say that minus over there can produce the 2, so it overwrites the old 2 and wakes up the neighbors, and so that minus can produce a 1 over there, which overwrites, and, well, now you could solve this problem, for instance, in Guy Steele's PhD thesis, the constraints were the basic units, and these little directed boxes were inferior creatures. You could solve this problem by looking at a single constraint and saying, well, if I just fired the plus, don't wake up the 2 inverses. So you could kludge around that, which isn't a very good idea, but you still have other problems. If you try to convert a Fahrenheit to a Celsius and a Celsius to a Fahrenheit at the same time, they'll fight like this. You don't want that either. This fight can go back and forth for a long time, and now there isn't as much of a sense of what's the core unit that you can tweak the scheduler to reschedule.
Could you talk about time in this? I mean, you're assuming
And that's the problem. If you say that a new value clobbers an old value, suddenly you've introduced time because something changes. You forget the old value, so there was something in the past that's now gone. And that's a problem. And so you lose for reasons like this. And that's why you start thinking about worrying about the scheduler, because now time is important, so the scheduler matters. And really, we'd rather avoid having time be embedded in our infrastructure if we can manage.
Question?
Another approach, I mean, like long ago, Chandy and Isra basically said that's fine as long as it converges.
Well, but that particular fight would converge to the wrong answer.
True. But they would claim that that's just not a very useful computation. It doesn't converge, it doesn't do that.
We'll solve their problem.
What?
We'll solve their problem.
Okay.
Yes, we'll do a little bit better than just don't do it.
We'll see.
A little.
Don't do it. It's a political phrase. Just don't do it.
So the last thing you could try to do if you're not aware of what the values are and what they represent is just forbid this situation completely. You know, if I already have a value and you give me another value, not allowed to do that. Well, that's even more of a bad idea because it just sweeps the problem under the rug and makes a really big bulge someplace else. Either you have to tweak the scheduler really hard to avoid these duplications, or you have to change the propagators so that they look in their outputs before putting something there. So you bite the bullet, and the least invasive thing you can do with a bitten bullet is introduce an equality test. So you had an old value, you're getting a new value. What do? Well, if the new value is equal to the old value, then that's okay. That doesn't cause a problem, and that shouldn't cause any recomputations. So great.
However, we've now pushed the problem into what equals means.
That's right. So this avoids the buzzing, and it avoids the fighting, because that signals a contradiction, which you sort of maybe want. But now you've baked in equality. That's not very nice. And now if you want to track the dependencies, you have to change the equality, or you have to change the cells. And you could get this nasty situation where, well, the cell used to have a 6 that is justified by decision A and decision B. But then something else came around from somewhere and said, well, actually, you don't need decision B. It's a 6 justified by decision A. Well, you kind of want to throw the old one away and get the new one. And maybe you even want to repropagate because you don't have this dependence on B anymore. But that's not equality in any sense. So maybe you bake that into your propagator. And then if you want to do backtracking too, you have to change something else because now these decisions can be undone. And this is, so you're tempted to do that. This is a disaster. And it's a disaster that appears inevitable. You had a value and you got another value. What can you do about it? Well, you track where they came from, remember all the options and all the dissenting opinions. It sort of feels like you have to do this.
Let's go to committee.
It's called a commitment, an ontological commitment that was wrong. And by that point, you've lost the essence. And you're building a very complicated system that has truth maintenance built into it. And if you want a different truth maintenance, you have to build a different system and think about it all over again. And we were down this rabbit hole. if you want to save any effort by trying to do something that looks like normal order and trying to pass requests around in order to decide which values you need to compute, this dependency tracking gets you into all kinds of trouble. Again, it's horrible.
Terry and I went very far down that path. And Alexi rescued us.
Well, no, I dug a bit deeper too.
Well, yeah, but you found a way out.
And this is the way out. Change the view. The perception of what a cell is about. A cell is not about a value. A cell is an accumulation of everything you know about that value, which much of the time might be less than a complete description of what the value is. Well, how does this address our problems? Now I introduce this function called merge, whose job it is to merge information you have. So a new value is just more information. That's wonderful. You dig up the information you had.
One of the previous slides, you had a one-way box, which was an absolute value box. Would this scheme make that reversible? So that if you had a 4 come into the output of the absolute value box, the input would be either 4 or -2?
You could. You could also stick a choice inside that absolute value box that would make a guess. Is it the 4 or is it the -4?
But
Could do
is
that
the-
too.
How would you, where would you specify that the knowledge about absolute value for this output produces these two?
Right.
Is that in that merge operation?
Yes. I guess you sort of spoiled the foreshadowing. You win by making the merge a generic operation that the user can extend. So then if the user wants this sort of absolute value branching handled specially, they can write that stuff themselves. Or if they want to make it part of the general, if they already have a guessing and backtracking mechanism, they can do it with the guessing and backtracking, have the absolute value function guess which of the two answers it is, or whatever. Right, where was I? Oh, yes. So you just merge. One nice thing about this is the emptiness test disappears, because a cell being empty is just a version of information. You don't know anything at all. So there's some distinguished value that whenever you merge anything into that, you get the other thing. Okay. Well, this isn't quite right, because you, in a sense, you still have all the previous problems, but just the solutions to them come out naturally. If you already had a 5, that means you know everything there is to know about this cell, about the value that's supposed to be in the cell, and that is, it's 5. Somebody else says, oh, this value is 5. Well, merge says, yeah, I knew that. That's fine. And that's where the equality test went, but now it can be more general than just an equality test. So we could write into the contract of this operation that if the new thing doesn't add anything to what you already had, then just return identically what you already had, so you can test it with, say, EQ, and then you can drop that on the floor and prevent the buzzing. Great. And the other problem, a contradiction is also a kind of information, rather severe kind, which says, this situation is impossible. Well, then you can have some object that represents that, and your merge can be required to produce such an object when it's trying to merge two things that are completely incompatible. And then you check that in here and signal a contradiction when you really have a contradiction. So in a sense, this is just the same as the previous code, but it now flows naturally out of the story we're telling.
If you've got contradiction as a possible value for a cell, can you then have something which combines multiple cells and says that this is a contradiction as long as one of the possible paths
Not sure I followed exactly what you said, but one of
Make a contradiction of value, which is your propagating.
so in fact, it is useful to make the contradiction of value because then you can support a no good as being a contradiction that is supported by some number of choices. And then that situation you can claim is contradictory, but then you can have the backtracker, you can force the backtracker to sort of always prevent those from ever being believed by taking out some of the choices that support these contradictions. I haven't really thought this through all the way. Contradictions feel a bit special in that any other information that a cell has about its value is local. You know, if you know that it's 5, well, this one is 5, great. But if you know there's a contradiction, suddenly that feels much more global. That a contradiction in one place, I think at least usually you want it to spread out and very abruptly get itself fixed.
He was, I was really questioning he was asking that. He was asking whether you have sub-networks that some of which can produce contradictions and others which not, and you have something that chooses among them. And I believe that certainly you can, of course.
Yeah, so you,
Yeah, you misunderstood the question.
yeah. Is that,
Yeah, I was sorry, I was just saying if you've got multiple sub-networks and each of them is kind of a model of the world and one of them realizes it makes sense, then you kind of, feed them all
yeah.
into something.
So I'm afraid of using the one special contradiction for that purpose directly.
You don't have to think about it that way.
But I don't. Yeah, I was just about to. Because one thing you can do is you can have a big guesser at the top guess which of these guys is going to get the right answer. Or guess, I should believe this one and this one and this one, say. And then if this one produces a contradiction, that contradiction is now not a raw, impossible, terminal, end-of-the-world contradiction, but it's a contradiction that's qualified by this guess. And then you can say, oh, well, that guess must have been bad. Forget it. So I think contradictions fit into truth maintenance very nicely because if you discover contradictions that are qualified by various decisions you've made in the past, you can know that that particular group of decisions is bad for wherever the contradiction came from.
Does
Yep.
contradiction really need to be treated specially here? Can't you just have contradictory information as an acceptable state of the cell? And then from one level back, you look at the state of the cell and say, well, that cell has a contradiction. Rather than, as I said,
You could. You could.
That actually is a way of getting away from the idea of contradiction as global. So basically you keep propagating, and what you look for at the end is there a contradictory dependency? Is there a dependency somewhere that's contradictory? And then you know, well, you not only know that you shouldn't leave that particular value to them, but why? Right?
Yeah.
But contradiction is special in the sense that if you don't detect it, you will keep propagating forever. It's a problem for anything false. You'll just keep.
That's true.
propagating separate. So you have to detect it enough to say, all right, I got to stop propagating now to save my system, and then go tell the guys who told me this data, you guys got a problem. It doesn't have to be global. At least the guys who make
that's right.
assumptions have to want to know that you guys have to find it out.
Yeah, there's something.
Right. You can deduce anything from a contradiction.
Sometimes you have.
But it did happen to us.
Yes.
Oh, yeah, it certainly happens a lot. There are cases where you can have contradictions that don't cause buzzing,
Yeah.
right? So it's
Both of those at once.
Yeah.
Hmm? Yes, exactly.
In this case, it's not value.
But
Not a reality.
But if you're less blasé about contradictions than Chris, you can catch them here and fail. If there's a raw contradiction that comes out to the top and you really have nothing you can do about it anymore, this is a mechanism by which you can crash if you want to. And this is a recovery of the thing we tried to do before that tried to prevent you from putting multiple values into the cell. Well, it prevents you from putting things into a cell that are just completely unresolvable with each other. And we sort of talked about this already, but this story recovers the dependency tracking story that we had before. There might be a cell that knows its value is 3, but this cell doesn't. What does this cell know about its value? It knows, well, if you believe the decision A, then the value is 3. That's something you know. And it knows something else. If you believe the decision D, then the value is 1. And there might be other decisions that might produce other values, and it doesn't know anything about that right now. That's fine. And if it stopped to think for a minute, it would be able to figure out that the decision A and the decision D are mutually exclusive. That's fine too. And so you naturally recover this dependency tracking and also the backtracking stuff by implementing a kind of partial knowledge that you can accumulate in these cells. And you don't have to change the propagation infrastructure to do this. And it can just flow along, and then the abhor can discover some no good that it doesn't like. And there are many different ways you can build it. You can have a special pile of no goods in the sky if you want, which you have to kludge around a bit in order to make it work right, but you can do it. You can try to push the no goods around as a contradiction supported by these values as something else you have in your cell, and that can propagate around. And there are lots of choices. You no longer have to decide what the right way to do backtracking is when you build your propagator network, because it's just a type of partial information. And that, in a sense, is the real moral of the story, that this change of worldview and making merge be a generic that the user can extend is a decoupling of the question of how do you propagate and what's the story for propagation from the details of, well, how do you actually accumulate information in a cell? And we get a nice bonus out of it. In principle, we could even use many different kinds of accumulators in the same network if we wanted. Well, something thinking about stuff one way over here and a different way over here. And maybe we'd have to do something interesting when they come together, but
Add the cells in order to merge, and then you can dispatch that too.
So interval arithmetic has been studied as a kind of information and is something you might like to propagate in its own right. And it fits into this model perfectly. And if your cells are taught how to hold intervals, you can have one centigrade thermometer that's not very good give you this blue estimate of the temperature, and you can have another Fahrenheit thermometer that's not very good give you this green estimate of the temperature, and you can deduce things from them. The propagators, of course, would have to be adjusted to be also generic on the interval arithmetic. You can do that. And now this former thing that used to be a race condition isn't, because maybe this guy fires first and gives you a green result, and then maybe that other guy fires second and gives you that, then the cell will merge them. In this case, the lower bound comes from blue and the upper bound comes from green. So you get a new interval. And it's different from both of the previous ones. So it can propagate back in both directions. And now you have better measurements on both ends. In all three scales, you have better measurements than either one thermometer gave you by itself. And it just works.
In a complicated network, how do you know you've got an answer?
What?
In a complicated network, I don't see a way of knowing you've got an answer.
Well, you never know you have the best answer you will ever have. You know that you have some answer. And if what you're doing with this answer is also a network, then if you later get a better answer, it will run after it and maybe catch up eventually.
Some problems have.
The only
like this AMP problem doesn't have some good answers and a better answer. It's got one answer, which there's 5 for.
Yeah, and that one sounds just fine.
Well, so you don't. You can look at it as having multiple answers if you like. There can be some wrong answer coming out that's supported by some guesses, and then as this thing keeps buzzing, it will have to retract some of those guesses. And if the thing on the other end that's reading the answer is aware of the possibility of retraction, then when the retraction happens, it will discard the previous answer and wait for a better one, in principle. Also, in practice, the scheduler knows when the propagators have stopped. You need an assumption for that, which is that if you've run a propagator once and then none of its inputs ever change again, it will never produce anything new. As long as that's true, then the scheduler is capable of knowing that they're all done.
Provided there are no loops in the system.
Unless, if it converges. I mean, if it doesn't converge, it doesn't converge. And you might be able to detect somewhere that it converged someplace well enough.
Yeah, programs always do that. One can always run a program to screw yourself.
Yes.
We're just getting rid of increasing the number of ways.
There are many, many different ways to write an infinite loop. This is yet another one.
The purpose of good language systems is to find new ways to screw yourself. So then we can keep, it's like the cottage industry, we can keep giving talks like this. Well, we not only have figured out how not to screw ourselves, we figured out new ways to screw ourselves. We can give a new talk next time.
This suggests that there isn't any such thing as a value, it's just a collection of constraints. I mean, saying that it's 5 is just a particularly concrete
Yes.
constraint.
Yes.
So,
That's why it unifies.
okay, so integral arithmetic is another class, but
Yeah.
you could just generalize and say the whole point is just moving the constraints around, and then merge has to say, well, I got these constraints and these constraints.
Yeah. Yeah, and incidentally, you can take this interval and that interval and subtract them and get something for this 32, but you know that the 32 is better, is more precise, so you can throw that extra interval away and it doesn't have to change the constant.
But maybe that 32 depended on something else.
Maybe.
A constant that, yeah.
Mr. Fahrenheit.
Yeah.
A couple things would be nice. One would be if the results were independent of the schedule, and
Right.
it'd also be nice if you knew what kind of merging would produce an answer. Have you thought about that at all? Especially scheduling worries me a little bit.
Right,
I can
so-
imagine a network where if it's done in one order, you get one answer. If it's done in another order, you get two different answers. It contradicts the first one.
We have actually had bugs like that. I think that the story is that there ought to be some relatively simple laws that follow from a formal treatment of information as being the contents of these cells that should prevent the history dependence. So that if you let the scheduler run for long enough, then it will converge to some fixed, predictable state.
Discounted floating point.
Yes.
The floating point violates.
Floating point.
Floating point will violate such laws.
It's a good start.
Well, I don't think it would depend on the generic merge.
Right, so you want the merge to be
If you just
commutative.
do a random merge.
Yeah.
then it-
So merge does have to do what information accumulation does. So
that's what I was sort of getting at, is what sort of axioms does it have to say?
right. So it seems like you want it to be commutative. So that if you knew P and you learned Q, you know P and Q. And if you knew Q first and then you learned P, you still know P and Q. And it's the same thing. You want it to recognize implications as much as possible. So if you knew P and Q and then you learned P again, you want it to stay P and Q and not wake up propagators because otherwise it could buzz for a long time. Would be
When you're monotonistic, you just run propagators.
Hmm?
But you you need a monotonistic condition on propagator. So basically,
Yes.
if you give a propagator more information, it won't give you less information.
Yes.
Otherwise, you could
Yes.
replace it too.
Maybe not. Although
Certainly, it shouldn't contradict itself later. If you ran it on some information, it gave you something, and then you improved its information, it shouldn't give you something contradictory.
Right, but I think even if it gives you less, then your scheduler may run further. You can't-
Well, if it gives you less, then the cell that receives it ought to ignore the less.
Well, that's true. Okay. So it's not contradictory.
But if it gives you something completely different, then you might lose. And if it gives you less, then there might still be race conditions. Maybe. But if you have nice, well-behaved merges and nice, well-behaved forms of information that obey all the sort of natural laws you'd expect from your logic class, then it should work. This is not a formal proof.
So you did lose some information though when the information came propagating back, right? You started off with a more accurate view of what the Fahrenheit interval was.
No, it was 50-something to 68. See? 59 to 68.
Got better, actually.
It got slightly better.
And what he's showing you is probably not what would actually be recorded as the information, right? That might be a deduction that was made from combining information come together.
Sure. So the original information would continue to be stored in that cell.
Oh, yes, as well. There it is.
I think for me, this is the final proof that backtracking is not an essential part of propagation. That we tell this partial information story and you get nesting for free. You had intervals, you have backtracking, and you just stick the intervals inside the truth maintenance system and have the truth maintenance system recursively call merge when it needs to deduce the consequences of believing all the things you currently believe, and boom. So in a more real situation, you'd have, that thermometer said this, and then that thermometer said this, and the merge is a consequence of believing both of the thermometers. And then if you later realize that one of the thermometers was broken, you can take that out and you still have the old thing. So that about wraps that up. The one thing that convinced me that the partial information story is essential is that if you think about the partial information story in the context of an expression language, you get something fairly dumb, which is that in an expression language, the values that, say, get returned from expressions come from only one source, which is the expression, which means there's no point in having them be partial because there's no opportunity for them to merge ever, because they always come from one source. The source's inputs were completely computed. Then the source runs its computation, and whatever it spits out is everything you're ever going to know about what goes in that place. And you can sort of simulate merging by having one place that has P and then another place that has Q, and then hooking them together with and then you have P and Q over there. But in an expression language, these are necessarily different places. And maybe you have some mutation or assignments that makes it look like they're the same place, but they're really still different. So this partial information story is only interesting if you have multiple possible sources, because when there's more than one source, then there isn't an only source which is responsible for producing everything. So the disparate sources can produce pieces, and then the pieces can merge, and the sources can collaborate to refine the stuff. So that's sort of the the realization that we realized over probably a year or so of me and Jerry and Chris hammering on this, that part of the essence of trying to do propagator networks is that the cells hold knowledge rather than just values. And this idea that they hold knowledge rather than values is only useful in the context of something like a propagator network. There's a bit of a digression. There's been a fair amount of research in things like that I believe are called blackboard systems as a class, where you have some big, usually global database of stuff you know and a bunch of little rules or whatever that find something in this database and apply themselves and discover something new. And that's sort of like a propagator network with just one cell. That's really very big, and lots of propagators that read and write it. So partial information is sort of useful, but only in this kind of context of multi-sourcedness. And that was the story I had prepared.
And one thing, that in prologue-like things with unification, there is some back propagation of information from things that combine. So in fact, that's one of the kinds of, it's another system type of system that has that, because of unification. The difficulty with that is it's almost always structural patterns that are basically unified.
So it basically has only one kind of information.
Right, they certainly don't have the generalization of an arbitrary merge.
So another advantage of backtracking that we didn't mention is that it's very space efficient, because the advantage of not keeping track of bad things is you forget everything. You have very little memory. So I would think if you use this naively in a situation where you end up kind of remembering everything and running out of space, is there things you do to control that? Is that an issue that?
So we have run into this. Basically, yes. For the time being, my answer is remembering nothing is one extreme, remembering everything is the other extreme. Once you have a handle on both extremes, you can choose where you want to be in the middle. And we're getting a handle on this other extreme. In principle, there are various tricks we haven't implemented yet for garbage collecting things that you know you're not going to need, like values that are supported by sets of choices that you already know are contradictory. Our prototype doesn't get rid of them. Our prototype also doesn't get rid of no-goods as well as you'd like. Large no-goods that are subsumed by smaller subsets. It gets rid of them mostly, but not quite there. But those are still perfect improvements in the sense that you can't lose by doing that. And then you could imagine, especially if you had some notion of prior probabilities, sort of how likely was this choice to begin with, you might be able to sort of have some idea that you were exploring a bunch of unlikely stuff and it didn't really work out and you don't think you're going to go back, so you can forget it. And if you ever do go back, well, you've just traded space for time.
Yeah, I'm curious about that. It seems to me that you would want to be able to parameterize your merge function by the value that comes in. Right now, your merge function is independent of the cells. You decide on the merge function itself.
Yeah.
Couldn't you, or it would be, I think that you could gain some additional power by having the merge function be selected by one of the values that's coming in.
Isn't that what generic dispatch does?
It's already generic, but it's not dependent on the dynamic changes in values. In other words, my merge function says, okay, greater of these two things. But I don't have something that says, well, then if C is 3, then my merge function is going to be greater of these two things. Otherwise, my merge function is going to be lesser of these two things.
Oh. Where's the C?
I don't know, somewhere else in the network.
And then you have higher from it.
Right. And the reason being, I'm thinking about the case of latent class analysis, where you're trying to determine classifications of objects where you know that they've come from some particular model that's generating them. So you have a model of a merge function, but what you don't know is the set point of the merge function. That's what you want to find out. I'll draw you a picture after this.
Well,
Oh.
tomorrow.
Actually,
You want
one
some-
more little bit. So we're publishing a paper on this subject called "The Art of the Propagator" in the International Lisp Conference coming up in March, and we're also going to produce a CCEL tech report, which contains a complete implemented prototype that does all these wonderful things. And I amused myself over the weekend by writing the stupidest possible search that solves Massieu puzzles, however one pronounces them. It's a. Can I get a
Go ahead, do it.
web browser?
While they're figuring this out, tomorrow we're going to tell you about the implementation. How to make this work in detail. This we do have working.
Yes, it works.
Let's use this.
Yeah, this is what I was looking for.
Yeah.
Oops.
Uh,
No script protected you.
What?
What? I guess I lose. So the puzzle is a rectangular grid of spaces that has white and black circles in it, and you're supposed to draw a path through the spaces that goes through all the circles, and black circles impose one local rule, and white circles impose another local rule. So I wrote a stupid little program that for every edge between two spaces just randomly guesses whether it's in the path or not. And then there are a bunch of propagators that impose the local rules, and an external loop that imposes the additional condition that the puzzle requires that the loop has to be a single path. There can't be multiple loops. The stupidest possible algorithm. Just guess every choice. No very clever optimizations, and it just worked. I solved the medium ones, interpreted in scheme in a matter of seconds, and then ran out of memory on the big ones because the heap isn't very big in MIT scheme. But the nice thing about that exercise was I wrote a very simple program that describes what the puzzle is, basically as simply as I could. Here are the guesses, here are the constraints, that's it, go. And separately in the background, implemented by the partial information style, which is truth maintenance systems, there's a SAT solver, effectively, based on resolution, that was implicit in my program, and it was good enough to do a decent job. I mean, just a direct chronological search, 18 by 10 is, 180 squares, 2 edges each, 2 to the 360 some odd choices. That's not good at all. But the constraints were local enough that it could cut out large enough pieces of search space that it found solutions reasonably promptly.
That's a variant on my theory for the very effective Sudoku solver, which is that you implement the constraints and then you randomly choose arrangements and just keep slicing parts of the search space out. according to the constraints.
Yeah,
so you get-
so I haven't actually done Sudoku in this machine yet. This Masu seemed simpler because the guess space is a little easier to deal with. So it works on top of everything.